Fermat's little theorem states that if p is a prime number, then for any integer a, the number a to the power of p minus a is an integer multiple of p. In the notation of modular arithmetic, this is expressed as a to the power of p is congruent to a modulo p. If we further require that a is coprime to p, or equivalently, a is not divisible by p, then we have a to the power of p minus 1 is congruent to 1 modulo p. We can use induction to prove the theorem for all non-negative integers a. The base case where a is equal to 0 is trivial, since 0 to the power of p is equal to 0. For the inductive step, we assume that k to the power of p is congruent to k modulo p for some non-negative integer k. Then we use the binomial theorem to expand k plus 1 to the power of p. If we write out the terms of this expansion, then we notice that all terms except the first and the last contain a factor of p. Specifically, when j is greater than 0 and less than p, neither of the terms in the denominator of p choose j include a factor of p. Since p is prime, this implies that the factor of p in the numerator is not cancelled out. Hence, k plus 1 to the power of p is congruent to k to the power of p plus 1, and by our assumption, this is congruent to k plus 1, which completes the proof. So what if a is a negative integer? Then we can write a is equal to minus k, where k is positive, and apply Fermat's little theorem to k to the power of p. If p is an odd prime number, then negative 1 to the power of p is equal to negative 1. If p is even, then it must be equal to 2. In this case, negative 1 to the power of 2 is equal to 1, but 1 is congruent to negative 1 modulo 2. Euler's theorem is a generalization of Fermat's little theorem. It states that if n and a are coprime positive integers, then a to the power of phi n is congruent to 1 modulo n, where phi denotes Euler's totient function. Phi n is defined to be the number of integers between 1 and n that are coprime to n.